So I was going to use the board because my first few things I wanted to talk about antimonides, which I could not put the slides because they are so old. They are like 1980s. And I wanted to show you some slides, what work we were doing in 1980s on antimonides and chalcogenides, and which may have relevance today. As you see, most of the systems that are being studied today, because of the new physics which has emerged from 2016 or so, is basically on systems which are planar, which have zirconium silicon arsenide type of structure. So you go back in history, zirconium silicon arsenide is probably first made in 1920s or 30s in Germany, if I'm not wrong. And entire world of intermetallics used to be around few labs in Germany and few labs in France. And very late in 1950s, it came to United States. So I was going to show some such structures, very interesting structures, nobody has studied so far, which have relation to the planar structures which are popular today. The planar structures which are popular today are called the 112, 111, and 113, I believe. But you can have 11, you can have 114. You can design many types of structures which are not yet studied. The physics has not yet been studied. And I must tell you before then that I am a solid-state chemist by training. And my emphasis mostly is on structure, designing new structures, how to make new intergrowths, how to make two layers combined. Can you make multi-layers, not the way in thin films, but multi-layers in a three-dimensional structure. So that's what I wanted to show you for some of the slides, because unfortunately I came very late, and those slides are so old in some hard disks. So let me come to the topic. Most of you know, and you are probably better experts than me on what are topological materials, etc. Started with the paper in 2006. And interesting thing is that they have brought the word nictide into the common literature. Nictide is the group of phosphorus, nitrogen, phosphorus, arsenic, antimony, and bismuth, which is of interest. As you see in most of these compounds, they have phosphorus, arsenic, etc., and they are very interesting. Of course, the next closest material is the group 6, group 16 by the modern periodic table. It's the selenides and tellurides, and mercury telluride was one of the first materials. So here I say that nictides and chalcogenides are very interesting materials, but as you know, selenium and arsenic are you have to handle very carefully. Phosphorus also you need to handle carefully. Some of the phosphides, as you know, are used as rat poison, and many things else can happen. So that is why many people use tellurium for making compounds, leaving selenium. That's why you have more things to do in selenium, because less studied. But tellurium again has a problem, because tellurium has the ease of tellurides to become tellurium metal is much more than selenides become selenium. So what happens when you do reaction, you will have tellurium metal at one end of the quartz tube or whatever tube, gold tube you are using for doing reactions which are air sensitive. So you are doing inside a closed chamber. It may be many times people do arc melting, etc. But purity of the sample depends highly on whether you have adventitious elements like hydrogen, carbon, boron, which come with unless you have an exceedingly good quality of glove box, you will have even hydrogen we have detected in many of the compounds of like this in intermetallic compounds. So, but it may not matter for certain bulk properties, but it will matter for certain other properties. So with this, let me tell you that this is the kind of work I started on arsenides. They are superconducting materials. Many of them are layered. So you can extend this. As you know, this is called 1,1. This is 1,1,1. Today, what is 1,1,1? is like zirconium silicon arsenide. This is also 111 based on zirconium silicon arsenide. You can have 111, 4 layers. Like that you can combine. This is 112, so today's 112 will be some compound like neodymium silver Sb2, or neodymium silver bismuth twice, or ytterbium manganese some antimony twice, or something like that. But you can have all these structures related to structures which have been studied earlier in many superconducting structures. So we started with this. Initial study we did with some selenides, which were non-centrosymmetric selenides. If they were of interest, there was some background literature known in superconductors, and they had this asymmetric spin-orbit coupling. So we did, here, collaborator is here, Sundaresan. We did some measurements with him, but we did many of these. A3, M4, where M is here is selenium or tellurium. So these kind of compounds are forming, but they are not layered. They are 3D structures. They have a cubic space group, and they can be made superconducting. They are ferromagnetic. Depends on the rare earth material. You can get ferromagnetism to superconductivity in some of these compounds. So some of these we have published. This is one example. It's in print recently. It's on cerium-3, selenium-4 is a ferromagnetic, and it has itinerant ferromagnetism. It shows. And there are some interesting properties. One can look into those properties. And we also looked at the spin glass type of behavior, looking at the AC susceptibility, the variation of the AC susceptibility, and getting the numbers using the power law fit and the Vogel-Fulcher fit to get numbers which kind of explain whether you have the canonical spin glass or the cluster glass. So in this system, if you want to just have a comparison of these chalcogenides which are non-layered, you can have superconducting metallic ferromagnetic itinerant ferromagnets, and with different TCs showing competing magnetism, and some of the properties we are trying to measure of some of these phases. But all of these papers are published. Then we also worked on this with Gautam Sheet. This was one of the beginning papers in this topology, this world of topological materials. For a chemist is very different, right? So when I was discussing with Gautam Sheet and this material he wanted, we made it, and then he could inject electrons, and we could convert cadmium-3 arsenide is insulator, and it becomes a superconducting material once you inject electrons, and you can do all Andreev reflection, etc., to see these properties. So this I will skip. All of you know what kind of topological materials are there in the world, and I'll come to this planar structures which have 4x4 nets, and this 4x4 nets in literature is quite old, and you will have in metals, people are talking about antimony, bismuth, but you can also find in selenium, in tin, you can get in tellurium, you can get these 4x4 structures. And of course the physics changes whether these planes are uniform, that is real for it's square, or it is distorted, and then the physics changes. So there are a lot of studies on that. I'm sure all of you, this meeting is, I believe, full of people who are working on these kind of materials. I'll just show some of the materials which we have followed. This is there in the literature, that how many types of materials. This is the one I am saying that many people refer to as the grand old man of 111 system is zirconium silicon arsenic. And then, of course, many types of compounds have formed. The very simple structure, you see, that you have these layers, and in between you have rock salt layers. So that rock salt layer is like sodium chloride, which gives you one metal, one X, and the other layer gives that other X or Y. So Mx is the rock salt layer, and the Y is the other layer, which is the planar structure. And you can get all kinds of these stuff. And this is the review by Leslie Shoup, who is right now in Princeton. She moved, right? So this is another structure, another slide to show that what happens in this 4x4 structure. You have this folding of the Brillouin zone, and you have these band crossings possible. Here I show 4 structures. Of course, 2 of them are similar. Both of them are 1,1,2 structures. This strontium manganese bismuthide. This is calcium manganese bismuthide. And both of them are referred to HFCuSi2 structure. That's because HFCuSi2 was the first structure which was solved. Structurally, it was solved long back. That's why you have, but there are hundreds of compounds which have this 1,1,2 structure. And this 1,1,2 structure, again, you have rock salt layers, and in between and top, you see this planar structure is there. So here in the plane, you have got manganese, and you can change for different species. This is 1,1,2, this is 1,1,3, so additional some layer will come. And of course, this distances are also very important, that you are matching the top layer with the rock salt layers which is inside, so as to cause less distortion. So we have been doing, like many others, many of these compounds. Many of my first compounds I will show you are mostly polycrystalline materials, and as you know, to do real certain physics, you need a single crystal. So some of the studies later I'll show you is on single crystals, but we could make a lot of compounds. Many of them were 1,1,1, 1,1,2, 1,1,3, which I focus, which are on planar nets, but we have also made some other compounds like ternary compounds, Ta2, Ni3, Te5, something like that. Then there is a compound like NbNiTe5, and we have made alternates of NbNiTe5, etc. So having square nets, if you have real square net, then all these properties people can see in some manner or the other. That depends on the correlations and many other factors which can host fermions, relativistic fermions which can show Dirac or Weil dispersion, all these properties which you may be having lectures on different, but all these are possible. And distortion is an important matter. So when you are playing with what you want to substitute, that is where you can control the distortion. So just to give a quick slide, these are all the compounds that we have made. Just if I don't have time, what are the properties? NDSBSE is antiferromagnetic, non-symmetric square net lattice, shows frustrated magnetism coexisting with a semi-metallic background. NDBIT has got also similar properties. It has symmetry protected topological band structure. Some of them we have also done theoretical calculations. SMSBSE, again same structure type, and many of these have short range magnetic ordering. Many of them have metamagnetism or spin reorientation, etc. Apart from that 1,1,1 type, we have worked on these compounds on 1,1,2, neodymium silver antimonide, praseodymium silver antimonide, gadolinium nickel antimonide, terbium nickel antimonide, and these 2 structures which do not form stoichiometric compounds. And there's a reason for that, why these always form zinc 0.65, 0.63, depending on the rare earth, and these also we have worked upon. So many of them, for example, the neodymium silver Sb2, we have grown single crystals and studied the properties. 1,1,1 type, we have all studied polycrystalline samples. These we could do a lot of detailed work, including anisotropic properties, rotational properties, etc., to map the Fermi surface. All that we could do with these single crystals. All of them we have worked on single crystals, and this we have already published. This we have, I think, communicated, and this also is, I think, accepted in Agile. The last type of compounds is 1,1,3. I will describe this one in some detail, and then we have also made this and this compound. So they also have the planar, and this is important, these are antimony. The nets are made of antimony. Most of the earlier ones were selenium, and they have all these interesting properties. Apart from that, I was saying we have also worked on something which does not have this kind close to this 111, 112, 113, but different stoichiometry, and this is already published, and it shows quantum oscillations. It's published in Journal of Applied Physics, and this we are going to publish very soon. So again, coming back, these are compounds we have published in these papers, 111, 112, 113. This was the starting point. We looked at this compound, and we tried to see that if we dope bismuth in antimony side, you can increase the spin orbit coupling. So that was the intention, to do this, and if you can add selenium instead of tellurium, then you can reduce the lattice size and you can increase lattice contraction. So these were the two starting points, and then we added more 111 compounds to this phase. So this is the structure, and these are the X-ray. This is more detailed if you want. This is the refinement. The structure is known to everybody, and these are planar nets of bismuth in this. These are the properties. The magnetism shows antiferromagnetic behavior. The Néel temperature is 3.3 Kelvin, and you can also see that you can, in the AC susceptibility, so as you increase the frequency, your peak reduces, so we don't find this kind of spin glass behavior. And there is a nonlinear chi behavior which we ascribe to the crystal field splitting parameter. So you can look at other properties, like we can look at the metamagnetic transitions, and they vary as a function of field, and you can get these transitions. You can measure the specific heat and get the numbers, the beta, gamma, and the theta values. So there is usually in all these, many of these 111 type of compounds, you see these metamagnetic and the spin orientation compounds. So we did these calculations, and these calculations I think was done, I forget, because we are collaborating with 2-3 people. I think Dibajyoti Ghosh from IIT, or Tufan Roy, who is in Tohoku University. I forgot who did this one. And the student who worked was Prabuddha. And here, as you see, that without spin orbit coupling, you have these crossings, and with the application of the spin orbit coupling, this goes away. But close to the Fermi surface, of course, some crossing is retained. Important thing is, if you use the spin orbit coupling with magnetization and without magnetization, this one is without and this is with magnetization, then you have more degenerate levels with magnetization. So this kind of going with the calculations and our understanding, it is type of a weak topological state in this bismuth-based square lattice. This is another case. That was NDBIT, this NDSBSE. So this is antiferromagnetic again. And here Tn is around 4 Kelvin. Most of them are at low temperatures. Here we studied this memory effect. So you stop at while field cooling. And we also did ZFC and wait for some time, nearly for an hour at 100K, and find the difference and plot the difference at 100K. So there are memory effect studies. This is the metamagnetism kind of. You can see the transition better in the derivative plot. Yeah, so it's saying 5 minutes. So these are kind of similar things. NDB, gadolinium antimony selenide also has similar properties. And you can see the spin reorientation temperatures. It is antiferromagnetic, and you can measure the magnetocaloric effect, and you can see the changeover from the inverse magnetocaloric effect to the magnetic caloric effect. And you can look at the arrow plots. It's a first order phase transition. And you can also look at the magnetoresistance, and you can see the positive magnetoresistance in this compound. The Hall measurement, shows a linearity, deviation from linearity, and so you can try to fit it to a multiband type of properties. We can measure the specific heat, and we have very large Sommerfeld coefficient. as well as, so which suggests a strong coupling, and you can measure other properties. So I will quickly skip. Samarium antimony selenide does similar properties. We have done all kind of measurements. You can look at the linearity of the magnetoresistance up till 14 Tesla. For SMSB SE, we similarly very large Sommerfeld coefficient, and again you have a multi-band nature of the plots. Here you can see basically the states at the Fermi level. They are being contributed by selenium, and other features are there. This is kind of a comparison of these three compounds: antiferromagnetic, metamagnetism, and some Kondo type of behavior from the resistivity plots you can get in these cases. Let me come to this one, which is a single crystal study where you have done anisotropic magnetic properties. So this is NdAgSb2. This is in print right now. And these single crystals, this is the work of Aarti. And we have done all kinds of measurements for this. And we get oscillations at very low magnetic field, right? It's below a 9 Tesla itself, we get reasonable oscillations, which suggest high mobility fermions are present in this, and a signature for non-triviality. We can look at close to the zero field, and we see that here some signature of linearity which suggests the weak anti-localization effect is also there in these kind of matter. So you can see the oscillations. From these oscillations, you can predict the nature of electrons below the Néel temperature, and above the Néel temperature, you can see the variation in the charge carriers and the carrier concentration. We have also done these measurements, out of plane and in plane measurements, and these were done at Tohoku University. And you can see that the in plane rotation gives, as you go, as a function of magnetic field, you get the kind of a plot which gives you the most anisotropic Fermi surfaces possible, whereas the out of plane rotation kind of does not give this kind of a twofold to fourfold kind of change in symmetry. So this is one case. We have also measured 113 example. I will give you one cerium nickel antimonide. This is in print right now, General Magnetism and Magnetic Materials. And this was done by Hari Brahma Singh, who is also in the audience. So you can look at the magnetization along different reactions. We can plot these and show the memory effect, aging behavior, the spin glass kind of behavior. These numbers below 0.3 suggest that it is a kind of spin glass, and doing this analysis, it comes to 10 to the power minus 10 to 10 to the power minus 11, gives you an idea that this may be more like a cluster glass behavior. And here also we did the transport properties. As you see, it's highly anisotropic shape, and it's also tilted, which gives you a signature of a non-trivial behavior. So we have got these spin orbit coupling gaps at the Dirac point. This appears to be a Dirac nodal line semi-metal, but currently RPS work is being done. But whatever from the data what we have, we are saying Dirac, but we are also in the mind thinking it is going more towards a wild semi-metal. And that will be proved when we get the RPS result. So I will stop here. We also have worked on lanthanum compound. This is my last slide on these two compounds. Thank you very much.
Thank you. So thanks for the nice presentation. So now it is open to questions. Yeah, please.
Yeah.
So,
Okay, you are.
How in your system there is a finite anisotropy in the system. So how have you separated this that you are saying that the magnetic resistance is due to weak localization. It can be due to anisotropy in the system.
Yeah.
So
For
how
that
can
we
you
have
separate these two?
we have done some measurements, but you are true that normally when you are there's also some kind of scattering. I think that's the physicists use that weak anti-localization and some scattering can be mistaken. But we have done some other studies. Right now the data is not with me, which kind of suggests that it is more weak anti-localization.
Can you suggest these measurements?
Yeah, sure. You can talk to me or write a mail to me.
Hi, Professor Ganguly, very nice talk. And I want some comment from you regarding these means radar-based topological systems. Do you always find a very high Sommerfeld coefficient here so that we can tell that the effective masses is always high and it's a strongly correlated region?
So if you look at our compounds and our published papers, we have very high numbers, all 150, 160, 240, whereas many reports report 10, 5, 4. So most of our systems are very high. This I can tell. Now I have to work back and tell you for a future combination which you should take. Actually, I thought I will have a time to put in some slides at some old, very interesting antimony structures.
A lot of rare earth stuffs.
Yeah, these are very simple structures. For a solid state materials chemist, these are the simplest structures you can work. But they are very interesting structures. I thought I'll write on the board, but
These are all single crystalline structures.
I said 111 is difficult to make single crystal.
Okay.
But 112 and 113 we have made all single crystal. But there can be infinite compounds you can make. You have just reinvented the wheel. What people were doing in 1930s to 60s, if you look at papers, now you can just look at many other compounds. See, for example, calcium 14, antimony 11 is their compound. Nobody is working. I'm just giving you an example. Calcium, say 36 or something, antimony, again some vague, but absolutely single crystal structure is known, everything. There's a lady in UC Davis, all her life she has worked on calcium 14, some metal, manganese, antimony 11. So many possibilities are there, and none of them have been searched for these kind of. So a lot of things can be done. But you probably would like to close to square net. I would like to see what happens if you have a hexagonal net, whether it will still retain that property.
There are oxybromides.
In which people have worked?
Rare earth oxybromides are hexagonal.
No, they have
I have worked.
not structure. Have they worked on non-trivial behavior?
Experimentally, they are synthesized, but nobody has seen.
That's what I'm saying.
Yeah.
Thank you.
So, any more questions?
So when you say cluster glass, both ferromagnetic and antiferromagnetic will be there. But why do you specifically mention ferromagnet as one cluster glass?
Okay. By the way, I am not an expert in this, but the number what we got after solving those Vogel-Fulcher law, that is suggesting it is a cluster glass and not a canonical glass. That is my understanding.
Okay, so let us thank the speaker again.
No problem.